Okay, good morning, everyone. Let's get started. Just a reminder of where we are and where we're going. Everybody finished up assignment 3, okay? Okay. There was a little confusion, mostly on my part, about assignment 3 and sensors, particularly that are placed into the root link. I've updated step 11. If you've submitted sensors, perfectly fine. I found in my code, I had torso as the root link. And just to recall, the root link is always the very first link that you save out into the URDF file. So in your generate.py, whatever the first link you send out, that's the root. And then everything else is attached below that using joints and so on. I found in my code, if I made torso the root and I put a touch sensor in the torso, no matter how much I smashed the torso onto the ground and pulled it back off again, there was still a constant value of +1 in the touch sensor value. Another student found the same thing for a different link, which was serving as their root link. So I updated this. My understanding was any touch sensor that's placed in a root link doesn't work. Of course, the minute the ink was dry on this, a third student came and put a touch sensor in the root link and it worked perfectly fine. So it's back to being a mystery. If you found that one of your touch sensors wasn't working, that's perfectly fine for the sensors assignment. Actually, it'll be a great object lesson when we get to evolutionary algorithms. As long as there's a few working sensors in your robot, your evolutionary algorithm will figure out how to squeeze whatever desired behavior you want out of your robot using the sensors that are available to it. Did anyone else have this issue? A constantly firing touch sensor in the root link? Yeah? Couple people? Okay. If anybody figures it out, please let me know and I'll update assignment 3 accordingly. Question?
I just had to remove the SDF box.
Ah, you removed the SDF box and that fixed it.
I could only get the sensor values to change if I hit it with the box.
Oh, interesting.
So I figured
Okay.
remove the box and then it worked.
Oh, that's interesting. Okay, so it's got something to do with the links in the SDF file. Okay, the mystery deepens. Anyways, it won't have any impact on what you're doing. Okay, so we're moving on to assignment 4 this week. Just as a reminder, for our purposes, we're focusing on 6 major building blocks of your robot: links, joints, sensors, motors, neurons, and synapses. You can probably guess what you're going to be doing in assignments 5 and 6. In the motors assignment this week, you're going to be incorporating open loop control into your robot. We talked about open loop control before. If you think about your robot as a set of sensors, and those sensors are being passed through the neural network, which controls how the robot transforms its sensor values into motor commands. What you're going to be doing in assignments 5 and 6, when you're adding in neurons and synapses, you're going to be doing closed loop control, meaning that whatever motor values are being spat out by your neural network, those motor values are going to apply torques, which we talked about last time. Torque is rotational force, so trying to rotate something. In our case, motors are going to try and rotate two connected links relative to one another. In closed loop control, the motor torques are going to impact the robot's relationship with its environment. And as the robot moves relative to its environment, its sensor values are going to change and you have closed loop control. This week you're doing open loop control. Open loop control where you have sensors in your robot, you don't have a neural network yet. You're going to be generating time series data, a value that changes over time, and you're going to take, at each time step of the simulation, you're going to take one of those values and just send it as torque to the motors. You're going to send it as a command to the motor. So this is, as you can see, open loop control. So the robot is basically going to ignore its sensors and it's going to just blindly do the same thing over and over again. Yep, pretty straightforward. Any questions about open loop, closed loop control? Okay. We're going to finish our discussion of physics engines today. We didn't quite finish that up last time, physical simulation. We're actually going to look at how motors are simulated in physics engines. So what we haven't talked about yet is when we get values at the output layer of our neural network, how do we translate those values into torques and forces that act on the joint, which causes the relative angle of connected links to change? I'm going to focus on that in a few minutes. Any questions about assignments? Assignment 3, assignment 4? All good? Okay. Back to the fun stuff. Physical simulation. We were looking at some code actually taken from a different physics engine that we used to use in this course last year, just to sort of highlight some of these basic ideas. We looked at orientation, and we talked last time about this very important concept about joint axes. Hopefully most of you had a chance to play around with that to understand how that works. Okay. And we ended last time by starting to talk about one of the most computationally challenging aspect of physics engines, which is collision detection and resolution. And we saw right at the end of class last time about why collision detection is so computationally challenging, because we have to look at, in the bottom right here, every pair of objects and detect whether they're close enough and in contact to resolve the contact. So we've got to detect whether pairs of objects are in contact with one another, and if they are, then the physics engine has to figure out what to do with it. There is a whole interesting literature on trying to make this process more computationally efficient. In ODE, and you can do the same thing in PyBullet, you can use collision spaces, and I've just created a cartoon example of this here. Let's imagine you create a particular simulation where most of the time some of the objects are relatively close to one another and another subset of objects are relatively close to one another, but they don't usually come close to one another. If you know that fact a priori, you can place subsets of objects in different collision spaces or contact spaces. So in this case, we placed 4 objects in space 1 and 5 objects in space 2. How many contacts, how many potential collisions do we need to detect in this case? When we discussed this last time, in the bottom right, we have 9 objects. We need to visit each of the 9 and see whether that object is in contact with any of the other 8, which gives us 9 times 8, or 72 possible collisions. But we can take that sum and divide by 2, because we don't need to look at the distance between object I and j, and then later look at the distance between j and I. It's always going to, by definition, going to be the same. So if we had 9 times 8 gives us 72, divided by 2 gives us 36 collisions we need to detect in this case. How many do we need to detect in this other case where we partitioned our objects into 2 contact spaces? 6 for space 1, so 3 times 2. We need to visit each. We need to visit all 4. Visit the other 3 gives us 12. Divided by 2 is 6. Over here, 10. So 6 plus 10 is 16. Are we done? We're assuming that these 2 sets of objects are close, within each subset, those objects are close to one another, so we definitely need to do those 16 detections. But we're assuming that these 2 sets of objects are also moving.
Do you have to check if the spaces are still not colliding?
There's one additional contact we need to detect, which is to put a bounding box around both sets and see if those bounding boxes are in collision with one another, right? Which gives us 17. As I said, we're assuming most of the time the 2 sets are disjoint, but maybe from time to time they come close to one another, and now their bounding boxes collide. If we find that the 2 bounding boxes are colliding, what do we need to do in that case? We can't get away with 16. We need to do all 36 like we did before. You don't need to remember the details of this. This is just an illustration that there's a lot of these hacks you can do to try and reduce the number of collisions, which makes things so slow. When you created your tower of links back in the many links assignment, depending on your laptop, you probably noticed the simulation started to slow down pretty quickly if you made lots of towers and you made very tall towers. This is why. It was trying to detect collisions between pairs of objects. And hopefully, if everything was working, it did it correctly. Pairs of objects where one was sitting on top of another in the tower did not start to sink into it. Yeah? Okay. So this is collision detection. Now we're going to talk about step 2 here. If they actually are in collision with one another, what do we do? Basically speaking, we're going to add additional forces to push the objects apart. Remember, at the deepest level of every physics engine is F equals ma, which is rearranged into A over A, A equals F divided by m. So we're going to compute all of the forces that are acting on each object. Most of the time, gravity is a constant force pulling all objects down. If 2 objects are in collision with one another, we're going to add additional forces that are temporarily pushing the objects apart until they're no longer in collision, and then those forces are turned off. Okay. Again, this is just some code taken from ODE, Open Dynamics Engine, the other physics engine we used to use. In that particular physics engine, there's a callback function. In this case, it's called near callback, and the name should give away exactly what this callback function does. At any point in time as the physics engine is running, if 2 objects are detected to be near one another, suddenly this function is called. And this is written in C. We're not going to go through all the details. What I want to point out here is it's looking at 2 objects, O1 and O2. It's looking for a couple of conditions. One condition it's looking for is, are these 2 objects connected by a joint? If they're already connected by a joint, don't try and push them apart, right? In the case of your robot where you're connecting the front leg to the torso, those 2 objects might be in collision with one another. The joint is applying forces to keep them together. If the contact resolution is applying forces that's trying to pull them apart, you'll start to see your robot jitter, and eventually it will explode. Okay. So there's a few things we need to do to make sure we actually need to detect this contact. If this contact actually exists and we need to resolve it, what ODE does and what PyBullet also does is it will sprinkle a number of points within the overlapping volume. So in this case here, I'm assuming we have 2 cubes, and these cubes have just come into contact with one another, and my cartoon drawing skills aren't very good here. Imagine the point at which they meet. There's a very, very thin wedge, and inside that rectangular wedge, it's going to sprinkle some points. And then for each of those points, you'll see there's a for loop here in ODE. It's iterating over all of these points, and it's setting various features that's going to determine the kinds of forces that push these objects apart. For our purposes, those features aren't very important. Just a couple things to notice here. If you try and pick out the English words here, you'll see bounce. So when 2 objects collide, if you get down into the engine room of a physics engine, you can play around with how objects respond when they come into collision with one another. If you're simulating some plastic bouncy balls, you can apply quite a bit of force when they come into contact with one another. If you're dealing with steel ball bearings and they come into contact with one another, you might want to apply relatively less force pushing them apart. There's not as much spring back from the collision. Obviously, in this course, we're going to hide a lot of these details, but for those of you that are interested in physics engine, you can enter the PyroSim directory and drill down into some of these files and actually play around with some of these things and see how it affects the simulation of your robot. Okay. Carrying on with the ODE code, at this point, we're going to enter another for loop, and this for loop is actually going to create contacts. It's going to create particular kinds of joints between these 2 objects. which seems strange. Why are joints now coming into our discussion about contacts? We were talking about joints connecting pairs of objects together and removing some of their relative degrees of freedom. So they restrict the ways that they move and rotate relative to one another. Why are we using joints in this context? It's our way of applying force. So the hinge joint, which we talked about last time, keeps objects connected together, but allows them to rotate relative to one another. Contact joints are just a different kind of joint that removes degrees of freedom in a different way. It applies forces to remove those degrees of freedom. In this case, the contacts are restricting a particular type of motion. What is it? Hinge joints keep two objects from moving apart from one another. What do you think contact joints do? They do the opposite, right? They keep them from further interpenetrating. So joints in general are trying to restrict the relative motion and the relative rotation of pairs of objects. Different kinds of joints restrict relative motion and orientation in different ways. Okay. All right, so we've talked about most of the physics that goes into a physics engine. When we use a physics engine to simulate robotics, we have to do some additional work to simulate the other components that are specific to robotics, like, for example, sensors and motors. So here's a screenshot now back to PyroSim and PyBullet. So we can start to exploit some of the underlying machinery of a physics engine to help us with the simulation of other robotic components like sensors and motors. So in the rest of lecture 6 here, we're now going to focus on robotics and looking for where in the physics engine we can pull out information or inject information into the physics engine to simulate these robotic components. If you go into PyroSim, pyrosim.py in the PyroSim directory, and you look at how PyroSim actually simulates a touch sensor for you, you'll start to notice some familiar stuff. So we're actually going to use the contact points that PyBullet sprinkles at the intersection between colliding pairs of objects, which we just talked about. So PyBullet is already detecting and resolving collisions for us. We can just use that information as it's being calculated to simulate, in this case, a touch sensor. Okay. I want to just talk about SimLoop here. SimLoop is the infinite loop that runs in ODE to simulate all the physics. In your case, in PyBullet, you're creating this for loop inside of simulate.py. Every time we pass through SimLoop in ODE or your for loop in simulate.py, there are a number of common things that need to be done by the physics engine. In the case of ODE, as you see here, it explicitly looks for things that are colliding. So this particular call here will detect everybody that's in collision and will sprinkle contact points as need be. In PyBullet, that's hidden from you. In ODE, there's a call to dWorld step. In your case, there's step simulation. We talked last time about what a single step in a physics engine does, right? It sums up all of the forces acting on each object and computes the new acceleration of each object in the physics engine, uses that acceleration to update the new position and the new orientation of each object. In the case of ODE, which is written in C++, C++ requires you to do some memory management. So in this case, it's throwing away or deleting all the contact points. So when a physics engine sprinkles these contact points during collisions, these are temporary joints. They only exist for one time step in the simulation, versus the hinge joints, which constrain relative motion of pairs of connected objects throughout the simulation. In the case of ODE, you are responsible for drawing what's going on in your virtual world yourself. In PyBullet, as you've already figured out, it does all the visualization for you. So one of the nice things about PyBullet compared to ODE is it does more of the work for you, which is why we're using it in this course. But again, this is just to get you started. For those of you that are interested in physics engines, one of the things you can do for your final project is rip out PyBullet and replace it with a different physics engine. It's not a trivial thing to do, but for those of you that want to tackle that, it's a fun thing to try. Yep?
I'm curious. Excuse me. I'm curious. So you step through the simulation, right?
Yes.
The frame rate, is that like, are the physics calculations, like, is that independent of the frame rate, or does that, like if you have a faster machine, will
Yep.
the simulation run faster?
That's a great question. So you're asking about frame rate, and I've deliberately not talked about time yet,
Yeah.
but let's talk about it now. You'll notice that in ODE, when it steps the world, it passes in this numerical argument. This is the step size. Step size is not, don't confuse that with the step size we talked about when we talked about evolution strategies. Completely different thing. In a physics engine, the step size is the amount of time that elapses between one step of the simulation and the next. And it's usually measured in seconds. So 0.05 here means when you run this code and you reach this particular line, all of the objects have a particular position and orientation. If you call dWorld step with 0.05, what you're telling the physics engine to do is to simulate 0.05 seconds of time elapsing between now, where all the objects are, and where they should be 0.05 seconds from now, right? So that's kind of the frame rate. If we make a smaller number, that means we make a more accurate simulator. It's simulating much smaller changes in position and orientation from one time step to the next. If you imagine very large step sizes, imagine we have two objects that are moving in the simulation and they're moving towards one another. If we have a large step size, you can get the following. The physics engine would actually miss the fact that they actually collided with one another. It would simulate these two objects passing through one another. If we have a much smaller step size, we increase the probability that there is going to be a step in the simulation. There's going to be a point in time in which the objects are interpenetrating, and the physics engine resolves that collision. So if smaller step sizes mean a more accurate physics engine, why don't we just set the step size to be arbitrarily small? It's a lot of work for your computer, right? So it's going to take much longer to simulate. Remember that in simulate.py, inside of that for loop, you have a time.sleep call, which puts your computer to sleep for a certain number of seconds. So when you're working with physics engines, time is a little bit confusing because there are two timelines. There's the actual amount of time here in our universe that passes from one frame of the physics engine to the next. If you time.sleep for a 60th of a second, then your visualization window is going to animate 60 frames per second. You're going to get a 60th of a second passing between each refresh of the visualization. But that does not mean that there is a 60th of a second passing inside the virtual world. You can set the step size for it to be more or less time elapsing. You can actually play around with these numbers. Obviously, you can play around with the argument in time.sleep. You can reach into PyroSim and you can find the actual setting of the step size. At the moment, again, that's being hidden from you. And you can play with larger and smaller step sizes. And again, it obviously depends on your computer. Okay. Another kind of non-intuitive concept that takes a little bit to wrap your mind around. Any questions about time inside the virtual world and our world? There's a third number to keep in mind, which is the total number of time steps. How many times you call your for loop inside simulate.py. You can simulate the same amount of physics by setting time steps to be 10,000 rather than 1,000. So you can increase the number of total time steps by 10. You could reduce the time step to 1/10 of its current value, and you'll simulate the same total amount of physics, just more accurately, but obviously it will take longer on your computer. All good? Okay. Okay, so we just looked at exploiting some of the calculations that the physics engine is already doing to simulate a touch sensor. One of the things you can do in the final project is you can build different kinds of sensors into your robot. And in order to do so, you need to figure out where in the physics engine to pull out relevant information to simulate that sensor. In my little cartoon example here, I've got a two-dimensional quadruped. We're looking at it from the side. And at this point in time, we can see that object 2, the back leg, is in contact with the ground. And the code here, again, this is from ODE. You don't need to worry about the code. And we've got an external object here from world.sdf. Imagine I wanted to simulate now a light sensor. I wanted to put a light sensor inside the robot. And we're going to assume that this object is actually emitting a light. It's a flashlight or a light source, like when we saw when we were talking about Bratenberg vehicles. How might you simulate a light sensor inside a physics engine, given what we've talked about so far? Distance. So one of the things that's obviously easy to do in a physics engine is at any point in time, you can query the position and the 3D position and the 3D orientation of objects. If we assume that the light sensor is sitting in the torso, at any point, at every step of the simulation, we can ask for the position of torso, the position of the light, of the external object here, the light source, and take the distance. And there's one last thing we need to do if we're simulating a light source. Recall Physics 101. How does light propagate out from a light source? Anybody remember?
It propagates out like in straight lines. So if something is blocking it, then you can't pick up the light.
Absolutely. So in my overly simplified cartoon here, there's no occlusion between the torso and the block, except arguably the front leg or the front part of the robot. So we're not simulating occlusion yet. You can get smarter and do some ray tracing. Somebody mentioned ray tracing last time. And you can actually start to simulate a light sensor that obeys occlusions and shadows. What else do we need to do?
Phase with the inverse square.
Thank you. Okay. So light propagating out from a source. If you are twice as far from that light source as you were a moment before, the light is not half as bright. It's a quarter as bright. Light falls off inversely proportional with distance. So again, this is code written in ODE, but you can do the same thing in PyBullet relatively simply. We're going to get the positions of two objects, in this case object 1 and object 4, and we're going to set the light level, the value, to be 1 over distance. So the further away the object is, the greater the distance, the lower the light level should be. 1 over the distance squared. Okay. So not a perfect simulation of a light sensor. We're still missing occlusion, but you can see how you can start to sketch out approximations of different sensors that collect different physical phenomena from the virtual world. What other common sensors exist in robots or your phones that we could start to simulate in a physics engine? Touch sensors are pretty useful for robots. Light sensors are pretty useful. Sound, okay. Sound is actually trickier. Why is a sound sensor tricky in PyBullet or the physics engines we've talked about so far?
You can have sound bounce off of objects.
Okay, sound bounces off objects. What else makes these physics engines? You can still simulate a sound sensor. It's just going to take you much, much more work than a touch or light sensor. Why? We're not simulating sound. So you probably figured it out already, but your robot is operating in a vacuum. There's no air pressure. So if we wanted to do sound well, we could probably approximate it relatively straightforwardly. We need to simulate something about propagation of vibrational waves through a medium. Tricky to do.
You could approximate like a gyroscope on its own.
So the accelerometer in your phone, right? What's the orientation of your phone? Very, very important for robots. You have accelerometers in you as well. Where are they and what are they? You have two. Your inner ear, right? So that gives you information about the orientation of your head relative to gravity. It's also tied up with acceleration. How might you simulate that in PyBullet? How would you simulate an accelerometer? Or let's call it an orientation sensor, something that just gives information about the orientation of the object.
You can get further orientation of the object and then compare it to like the world plane, which is not going to change orientation.
Absolutely. So we talked about orientation. Orientation is actually specified with 4 numbers in most physics engines, but for a lot of purposes, we can throw away the 4th one and use 3. So you can use 3 numbers to represent orientation. So maybe you have an X, Y, and Z orientation sensor. You add 3 sensor neurons to your neural network. Okay. One way to review what we just talked about in this lecture is to think about the different sensors that exist in your car, on your phone, in your Roomba, and think about how you might try and exploit the physics engine to simulate those different kinds of sensors. In our purposes, you're going to work through all 10 assignments, only making use of the touch sensors. If you want, for a final project, you can try and implement other kinds of sensors and see if that makes it easier for the evolutionary algorithm to evolve desired behaviors for your robot. Okay, let's talk about motors now. This is the last piece. So we're going to, in motors, we're going to attach motors to joints. Remember that joints are controlling, actually we're going to focus on hinge joints for the next few weeks. Hinge joints restrict the relative rotation of connected pairs of joints. How does it do that? Well, when we attach a motor to a joint, that motor is going to apply torque that's going to try and extend or flex the object, the connected pairs of objects. So we're going to talk about flexion, and flexion is going to be any rotation that brings body parts of the robot or a human towards the center of the human or the robot. We're going to talk about extension as forces that try and push objects or rotate objects away from the center of the human or the robot. At the moment, you have joints, but you have no motors attached to those joints. This is known in physics engines as ragdoll physics, for an obvious reason. Your robot at the moment is a ragdoll, and you've been actually grabbing it and throwing it around. And through its passive dynamics, there's no torques being applied yet. There's no internal forces being applied by the robot to its body. You can see a lot about whether you've got the joints right, the links right, the sensors right. In assignment 4, when you start to add motors, we're going to motorize, obviously, your robot. It's no longer ragdoll physics. Okay. So how do we do this? Let's take a cartoon example here. Let's go back to my cartoon quadruped in the top left here. We're going to assume that the front leg here, which is off the ground, is attached by a hinge joint to the torso, and it's attached at the shoulder here. We're going to assume that there is a motor attached to this joint, and at this particular point in time, it's going to apply the motor is receiving a desired angle. Why desired angle? Because at the moment when we create our robots, we're going to create our motors, we're going to make use of position control. In robotics, a robot is often controlled by position control or velocity control. A robot that is positioned control means that at every time step, the motors are receiving a desired position. This is a little confusing. For our purposes, position is just going to be angle. There's a particular desired angle we want to reach. We could imagine that instead of a position or a desired angle, actually position makes more sense when we're talking about pistons. So if we have 2 objects that are attached with a piston, a position might be a desired position that we want that piston to contract or extend. In the case of a hinge joint, the quote-unquote position is an angle. Alternatively, in velocity control, you can imagine you have a robot, same set of motors, but the numbers that are being received by the motors at that point are desired velocities. A neural network controller could be communicating with a motor saying, I want these two pairs of objects to start rotating relative to one another at a particular velocity. That's velocity control. We're going to focus on motors receiving a number where that number is, I want these pairs of objects to rotate to a relative angle relative to one another. Okay. So when we create a motor, again, this is code taken from ODE. It's done differently in PyroSim. We need to set a number of aspects of that motor, like we did for sensors and joints and links. One of them is the total amount of force that the motor can apply. One of the things we're going to touch on in this course, but not spend too much time talking about, is how do we build more reality into our simulated robot? Obviously, motors and muscles in reality don't have infinite strength. In the Xenobot project, our first attempt failed because we simulated overly strong frog muscles when we were making our frog bots. And our evolutionary algorithm came up with simulated Xenobots made from overly strong frog muscle tissue. And we had Xenobots that were bouncing around in the physics engine. And when our microsurgeon looked at these simulations, and he was going to try and build some of these, he immediately said, there's no way I can build that. Frog muscle does not work like that. Frog muscle has a certain amount of force that it can apply to neighboring patches of tissue. So we built that into our simulation by decreasing the maximum force of the motors in the physics engine that was being used to simulate the Xenobots. Okay. All right, we're going to assume we're doing position control here. So obviously I'm hiding the neural network for the moment. We're just going to assume that this motor at a particular point in time in the physics engine receives a desired force angle of 60 degrees. Where did this desired angle come from? We're going to do this as follows. We have our desired angle of 60 degrees, so we want this front leg to extend out by 60 degrees. That's what we're basically assuming the motor is being asked for at this point in time. In the very first time step, when we connect pairs of links together, no matter the angle at which we initially connect them in the physics engine, that becomes an angle of 0, which is again a little bit confusing. This looks like minus 90 or plus 90. Doesn't matter. It's all relative. So if you connect two pairs of objects like this together, their relative angle is 0. Okay? In this example here, we have the front leg, which is dangling down vertically from the horizontal torso. It looks like there's an angle of 90 between the torso and the front leg. For our purposes, the relative angle is 0. Okay. We're going to talk about extension, rotations away from the center of the body, and flexion, rotations toward the body. We're going to try and keep things simple in this course. We're going to assume that positive numbers mean positive angles of extension. So positive is extension and negative is flexion. So at this point, when the motor receives plus 60 degrees, the motor knows that means it should be rotating the leg outward and away from the center of the robot. Yeah? You're going to eventually be building robots with different body plans, humanoid robots, dog robots, snake robots, spider robots. Keep this in mind, and it'll keep things simple and consistent across all the 60 different robots we're going to make in this course. Okay, so that's the desired angle, but So the motors receive as input an angle, but what motors supply as output is not angles or velocities, it's torques. It's going to, the joint is going to apply, the motor is going to apply a rotational force. It's going to apply torque to try and rotate these objects relative to one another. How does the motor take a desired angle and figure out what torque to apply so that at some point in the not too distant future in the physics engine, that leg is going to reach a forward extension of 60 degrees. The way we do it is to take the current angle of the joint, the actual angle, which we're going to pull out of the physics engine. So you can query a joint and get the current angle, the current relative angle of the two connected links. And we're going to take the difference between the actual angle and the desired angle. How much difference is there between the current angle and the angle the neural network wants the motor to achieve? The greater this difference, the more torque we apply. Make sense? This is known as position, I mentioned position control already. This is a little confusing. This is often known as a P controller. The P now doesn't stand for position, it stands for proportional. We're going to apply torque proportional to the difference between the current angle and the desired angle.
Does the torque cut off early, so it like stops right at the top position where you expect?
Good question. You can see where we're going with this. Things are a little bit tricky because we're only talking about the current time step. At the current time step, actual angle is 0, desired angle is 60, the difference is 60 degrees, and that difference is going to dictate the amount of torque we actually add. We're going to add torque proportional to this difference. As we're going to see in a moment, P controllers are not sufficient for the reason that's already been pointed out. I'm not mentioning in this cartoon the actual amount of torque. It doesn't really matter. We're going to apply that some torque is applied. Remember that torque is rotational force. So we got a new force now that's being added to the pairs of links that are connected by this joint. F equals ma rules everything in the physics engine, right? So we've got these new rotational forces that are acting on these pairs of objects. And in my cartoon example here, that torque has caused the front leg to extend outward by only 20 degrees in this case. So the new actual angle at this next time step is 20 degrees, but the desired angle is still 60. So now the difference is less. 60 minus 20 is 40. The difference is less. We're using proportional control here. So we're going to calculate the new torque that's applied is going to be less because the difference is less. So you can see what happens. Actually, this cartoon's a little bit inaccurate. It should be a little bit less at this next time step. So between the first and second time step, we've swept from 20 degrees to 20 degrees, from 0 degrees to 20 degrees. At the next time step, we're adding a little bit more force. So it's going to be 17 degrees, 14 degrees, 12 degrees, 8 degrees, 6 degrees, 2 degrees, 1 degree, 0 degrees. And we're going to reach 60 degrees, right? So it will stop when it reaches that particular point. Yeah? Okay. Question?
When you're using the position control from the physics engine to handle like negative angles if you want to go the opposite direction?
Absolutely. So in this cartoon here, imagine that the neural network, which I had drawn before, the neural network sends a value of minus 60 to this shoulder joint. Minus means flexion, means rotate inwards towards the underbelly of the robot. So what happens at this point, the desired angle is 60 minus 60 minus 0. It's going to apply torque in the opposite direction, and it's going to pull the joint inwards by minus 20 degrees. minus 35 degrees, minus 37, minus 43, 54, minus 60 degrees, right? So remember that the value that's arriving at the motor is a desired angle. That does not mean that immediately at the next time step that the links are going to teleport to exactly that rotation. It takes time.
So is the back leg also, if you put in a 90-degree angle, will it go underneath or will it go back?
Good question. So let's talk about, imagine there's a hip joint here. There's a motor attached to the hip joint. If we send a positive number to that motor, remember that positive is interpreted as extension. So what is the back leg going to do if it's receiving a positive desired angle? It's going to rotate back and away from the center of the body, right? Extension is always away from the body. Flexion is always in towards the body. So if we sent 60 to the shoulder and minus 60 to the hip, they're both, sorry, did I get that? No, I got that wrong. Plus 60 to the shoulder, plus 60 to the hip, they will both extend away from the body. Question?
Do we have to tell the physics engine what direction extension and flexion are? Or do we figure that out?
Good question. So will the physics engine figure out extension and flexion? The answer is no. It depends on how you set the joint axis. So if you find, when you're playing around with the motors assignment, you send a positive number and it flexes, go into PyroSim and change the joint normal. Okay? If this is confusing, we can talk about it more Thursday morning. Remember that the joint axis is a vector that is normal to the plane, the 2D plane, through which pairs of connected objects are connected. If we want our two objects, our two links to rotate like this through this particular plane, there are two possible joint normals. This one that points in this direction, and this one that points in this direction. If you set the joint normal like this, and extension, positive numbers cause it to flex, which is wrong, switch the joint normal to this. Make sense? If it's confusing, come back with questions on Thursday and we can do a worked example. Question?
That ends up not mattering, right, once it starts to be the neural network that's feeding value.
Great point. Once the neural network takes over, the neural network is going to start receiving positive and negative numbers at the output layer, and those positive and negative numbers are going to be sent to the motors. At that point, you can relax. Who cares, right? The neural network will figure out what numbers cause what body parts to move in what direction. For the purposes of assignment 4, to make your life easier and to make Krishna the TA's life easier, to make my life easier, positive numbers extend, negative numbers flex. All good? Okay. For those that are interested in this topic, I'm just going to mention this. It turns out that P control often is not enough. Depending on the step size, which we just talked about, you can get a leg that's rotating and slowing down in its rotation, but it might actually overshoot. It might overshoot an extension of 60. And now we got to apply a new desired force to pull it back again, and you get a joint, or you get a leg that is wobbling around some desired angle. So there is a more high-powered set of control algorithms called PD control, proportional and derivative control, which I'm not going to get into. But PD control is designed to make sure you don't get this overshoot. You get something that's smoother, rapidly approaches, slows, and then stops at the desired angle. Turns out that PD control, in a lot of cases, is also not sufficient. And there is one more set of controllers called PID control, proportional integral derivative control. Again, we don't have time to go into the details of this, But this is the gold standard. If you're driving your car and you start to slip on the ice on the road and you slam on your brakes are doing a lot of complicated things. One of the things they're doing under the hood is proportional integral control. When to apply and release torque to the wheels to make sure you slow as quickly as possible and come to a dead stop. Depending on how fast you're going and what's happening with the wheels. Things get very complicated when we're talking about very fine control of motors and moving objects. We don't have time to go into this topic here. Question?
So when it moves to the new angle, does that become like the new zero?
It doesn't become the new zero. So 0 is the angle between the two objects at t equals 0 at the beginning. Once they start moving, the number changes. So in this cartoon example here, the actual angle is 0. In this cartoon example here, we're assuming that the leg has extended forward by 20 degrees. So if we query actual angle at this time step, the actual angle is 20. If instead, starting from 0, we had applied a negative number that was flexing the leg, rotating it inwards towards the underbelly of the robot, it might have swept inwards or flexed inwards towards minus 20. So in this cartoon example here, if the leg were to rotate all the way out and was pointing horizontally forward, the actual angle would be positive 90. If the leg flexed all the way inward and was sitting underneath the underbelly and pointing backwards, that would be an actual angle of minus 90 degrees.
What would happen to the applied torque if you had a collision between your legs?
Absolutely. So let's imagine both legs are flexing inward. This is a great example. Okay, so they're both rotating inwards and upwards towards the underbelly of the robot, and the 2 feet come into contact with one another. What happens? Given what we now know about physics engines, what happens? Any ideas? They are not connected to each other. The front leg and the back leg in this example are not connected to one another. Each is connected to the torso. They are obviously indirectly connected through the tree, but they are not connected to one another, which means they should not interpenetrate. What's going to happen? What is the physics engine going to do?
Will the motors apply proportional torque at the opposite direction to make sure that they go into each other?
Motors don't care about collisions. Motors just do what we just talked about. They're going to apply a torque proportional to the difference between where you want to be, the angle you want to be, and the current angle that you're at. So if the desired angle is minus 90, it's trying to flex the front leg up and under the underbelly, but it's being blocked. It can't reach that desired angle. The motor is applying a constant torque. The difference is constant. So it keeps trying to rotate the leg inward and upward. What else is happening elsewhere in the physics engine?
So doesn't it just get stuck because it keeps wanting to apply that force? So nothing happens because it's stuck in a loop.
Okay, so nothing happens because the torques are frustrated, or the motors are frustrated. They're applying a torque. But these are in contact, right? So the physics engine at every time step is sprinkling contact points where the 2 feet are interpenetrating. And those points are applying a force in the opposite direction, trying to push the feet apart. And the motors are trying to pull the feet closer together. So we have 2 sets of opposing forces in the physics engine. This happens all the time. If you create a single link and it falls and comes into contact with the ground, gravity is pulling downward, and the contact points that are sprinkled on the undersurface of the object where it's in contact with the ground are pushing upwards. And hopefully these 2 sets of forces balance out and the object no longer moves. It's resting on the ground.
Is that how you did the arms of the robot that grabs the object? Just continually let them bounce until there's something between?
Oh yeah, so the example I showed at the beginning of the course with this robot that grabs the blue object and lifts it, in that case it was closed loop control. So the neural network was sending desired angles to the grippers, but those desired angles were changing. We're going to talk about that in a moment. We haven't quite got there yet. In our simplified example here, we're assuming that the desired angle is always the same. The torque might be changing if the difference between the desired angle and the actual angle is changing. But in this cartoon example, desired angle is constant. Okay. In most modern physics engines, in this cartoon example, everything would balance out. The legs would get stuck under the robot, and there'd be no more relative motion. In the old days, before physics engines had been perfected, the contact part of the physics engine would say, wait a second, I'm trying to separate these objects, and at the next time step, they're still interpenetrating. I'm going to sprinkle more points, and I'm going to apply a little bit more force. The motors see that these objects are frustrated, and it starts to apply more torque. The motors say, I was told to get the two legs to -90 under the body, and I keep failing. So the motors are going to start to apply more force, and the amount of opposing forces started to grow and grow and grow, and then the robot would explode and become unstable. If you go to YouTube and you Google physics engine fails, you can see all sorts of these things going wrong. It's actually super hard to get all these forces to balance and get a stable simulation. Tricky to do. Okay, as promised, let's move on to the last piece of simulating a robot in a physics engine. We've talked about simulating links, joints, sensors, and motors. Now we need to move on to neurons and synapses. How do we simulate a neural network that transforms virtual sensor values into desired angles that are going to be interpreted by the motors as torques? Okay, so let's go back to our cartoon 2D quadruped here. We're going to assume in this case we've put a very, very simple neural network inside this robot. We're going to assume we have two touch sensors in the front and back leg, as you just did in assignment 3. So we have two sensors, which means we have two sensor neurons or two input neurons to our neural network. And we're not going to bother about the hip in this example. We're just going to focus on the shoulder joint. We're going to assume there is a motor attached to that shoulder joint. We have one motor in this cartoon example, which means we have one motor neuron or one output neuron. No hidden neurons, no anything else. This is about as simple as you can get. Two sensor neurons, one motor neuron, and we have two synapses attaching both sensors to the motors. So far, so good? So not so different from the Bradenberg vehicles we saw a couple weeks back. Yeah? Okay. All right, we're going to run this physics engine in our mind to see how this works. We're going to assume at t equals 0 that both feet are in contact with the ground, which means both touch sensors are firing. They're both positive. They're both positive 1. We take those two sensor values and we plug them in to the two sensor neurons. In my cartoon example here, I have not told you the weights of these synapses, but we're going to assume that whatever those weights are, the final value arriving at the motor neuron is 60. We also are going to throw away activation functions. Remember, activation functions would squash the raw sum, the weighted sum arriving at a neuron. We're trying to keep things really, really simple here. No activation function. So we have a value of 60 arriving at this motor neuron, which we are going to send to the motor, and the motor is going to interpret that 60 as desired angle, as we just talked about. So this is the robot's brain, the neural network, saying, both feet are in contact with the ground. At that point in time, I want the motors to apply a torque to start rotating the front leg outwards towards, to rotate the leg outward towards plus 60 degrees. So far, so good? Okay, we just saw how the motor does that. So at the next time step of the simulation, the torques have been applied and the leg has started to rotate forwards. It's not at 60 yet. Let's assume it's at plus 20. The front leg has rotated forward, which means the touch sensor in the front leg has now turned off. This is now closed loop control. We had values in the sensors. Those sensors flowed through the neural network to the motors. The motors applied forces. Those forces acted on the robot and its environment. So the relationship between the robot and its environment has changed from the first time step in the simulation to the second time step in the simulation, and it's caused its sensor values to change. The minute these sensor values changed, we've traveled one cycle around this closed loop. So far, so good? Okay, so this is the first time we've seen all 6 of these pieces put together. Any questions at this point? So far, so good? Okay, here's where things get fun. Now that the second touch sensor has changed, the values at the input layer of the neural network controlling the robot have also changed, right? We take these new sensor values, we plug them into the 2 sensor neurons, and we have different values at the input layer of the neural network. We take those 2 values, we multiply them by the weights of these 2 synapses, and we take those 2 multiplied numbers and sum them together. And in this cartoon example here, I'm assuming the raw sum, the weighted sum that arrives at the motor neuron is minus 90. I've made one other simplifying assumption here. In your code, touch sensors are either +1 or -1, in contact or not in contact with things out in the world. In this simplified example, we're assuming touch sensors are either 1, the object is in contact with something else, or 0, it's not. What's the weight of the left-hand synapse here? What must it be if the input is 1, 0, and the output is minus 90? Minus 90, right? Okay, so this weight is minus 90. 1 times minus 90 is 90. 0 times question mark is 0. Let's go back a moment in time. Let's come back over here. This is the same neural network. We're assuming from one time step to the next, synaptic weights are not changing for now. This robot is not learning. The synaptic weights are fixed. So we know the left-hand synapse is the weight of the left-hand synapse is minus 90. What is the weight of the right-hand synapse? 150. 1 times minus 90 is minus 90, plus 1 times 150, minus 90 plus 150 is 60. Okay, this was just a prod for you to remember what synaptic weights are doing. So at t equals 0, the neural network is telling the motor, extend to 60 degrees. But at the next time step, the neural network is saying, no, I changed my mind. Motor, I want you to flex inward, negative number is flexion. I want you to flex inward towards minus 90. What happens? What happens at the next time step, t equals 2? We just talked about t equals 0, t equals 1. What happens at t equals 2? Okay, if at the next time step it gets back towards the ground, then we're back here, and we now have an oscillatory pattern. We'll talk about that in 2 minutes' time. But before we get there, remember that the front leg has mass, and it's at the previous time step, it just started accelerating or rotating outwards. So what happens at the next time step when the motor says flex inwards towards minus 90? What is the front leg going to do? Forget sensors, motors. Let's just think about the raw mass of the robot.
Will it start slowing down the leg and start stop?
It's going to slow down. Remember that the motor is applying torque, okay? It's applying force, F equals ma. There's acceleration, momentum, inertia going on here. This is not magic. It doesn't suddenly start moving in the opposite direction. That leg now has forward momentum. So a torque that is now trying to flex is trying to flex the leg, try to pull it inwards, the only effect it's going to have is to slow down the extension of the leg. So let's talk about, so at t equals 2, we now have the leg, which is actually still extending outward. It's just extending outward by a lesser amount, right? What happens with the sensors at that point in time? What's the state of the sensors at t equals 2? What's arriving at the input layer of the neural network at t equals 2? The same as t equals 1, right? So the back leg is still on the ground, and the front leg is still rotating forward. It's still off the ground. So at this next time step, the neural network actually has the same set of values. So what are the motors trying to do at t equals 2?
Travel to -90.
They're still outputting -90, right? The input layer hasn't changed. The robot is moving, right? But from the point of view of the neural network, which doesn't see that motion, it only sees the values of the touch sensors, nothing has changed. So the output is still -90, which means the torque of the motor is still trying to flex the leg inward towards -90, which means the leg is going to slow down even more at t equals 3, slow down t4, t5, t6, t7, t8, stops rotating forward. T9, T10, T11, T12, it starts accelerating inward. And it starts flexing inward. And as it does, it's probably eventually going to come into contact with the ground. And whatever time step that is, time step 17, time step 174, at that point in time, we're back to the state of t equals 0. Now both touch sensors fire again. The input to the neural network changes to 1, 1. The motors now say extend, right? Now we've got a tricky situation because the leg has hit the ground and now there's friction. We haven't actually talked about friction yet. Friction slows things down. So the leg is actually going to slow down because of friction and because the motor is now trying to rotate it back out again. So it's going to slow down pretty quickly and start to go back out again. And we're going to start to get a front leg that rotates forward and backward with a relatively stable sinusoidal pattern. Where is the sine function in this? There isn't one, right? This oscillatory motion is emerging from the interaction between the robot's body and its neural network controller. This is the foundation for embodied cognition. You get interesting things that come out of physically embodied things like humans and organisms and autonomous drones, autonomous cars, robots, when they start to interact in interesting ways from the environment. We could have got that front leg to oscillate with some frequency and amplitude with open loop control, which is what you're going to do in assignment 4, by sending in a desired angle according to a sinusoidal pattern, right? We could have programmed it in. We didn't have to. We got it for free in this situation. What evolutionary algorithms are going to do is they're going to sculpt parts of the brains of your robot and its body in order to produce some of this behavior for free. I don't think we're going to get to it today, but we're going to talk about some early experiments in evolutionary algorithms in the next lecture, and you're going to see a more complex example of this interesting emergence. Okay, that concludes lecture, what are we on? Lecture 5? Lecture 6? Lecture 6, physics engines. All good? Okay, we got 7 minutes left, so we are going to just start in on lecture 7. The very first pair of experiments in evolutionary robotics. In this theme, as you can see here, we're going to look at the history of evolutionary robotics. Evolutionary robotics is a relatively young field. We're going to go all the way back to the mid-90s to look at these first experiments. When you take a calculus class, you start in the 16th or 17th century, right? Okay. Relatively recent branch of robotics. Okay. We're going to look at 2 different experiments. The first one has become known since as the Italian approach. The second one, known as the English approach. We probably won't get to the English approach today. We'll focus on the Italian approach. This was done using a physical robot. This was before physics engines were in widespread use. It was conducted by 2 Italian researchers in Switzerland, so it's a little confusing. These 2 Italian researchers used this particular physical robot here, known as the Kepera. You can still get versions of the Kepera, I think, on eBay and Amazon. They're about the size of a hockey puck. And one of the nice things about the Kepera, first of all, is that it was very small, so you could do experiments on the top of a table without too much problems. And it was also built in a modular fashion where you could stack additional sensor and motor modules on top. In this little cartoon example here, they've snapped, in the top right here, they've snapped a little gripper on, and that gripper has grabbed a little sugar cube and lifted it onto its back. That should sound familiar. The robot you saw at the beginning of the course was inspired by this. The Kepera, the design of the Kepera should also look kind of familiar. Where else have you seen this basic robot body plan before? So a little disc-shaped robot with one wheel left, one wheel right. Sorry? For those of you that have a Roomba, flip it over. This is what it looks like underneath. Anybody know what the robots in the bottom right are? Also kind of disc-shaped. One wheel middle left, one wheel middle right. How many of you have bought something on Amazon in the last few weeks? If you have, it was sitting on one of these yellow shelves in some warehouse somewhere in the continental United States. But that shelf might have been buried in the back of the warehouse. So these little orange robots, they drive around, they drive underneath these stacks or shelves, lift them up, and then drive and pull these shelves out. Kind of an ingenious design. There was decades of work trying to figure out how you would create a mobile robot inside a factory or inside a warehouse like Amazon, where it could actually help find objects, take them off the shelf, drop it in a bag or a box, and have it shipped out. This was the solution that was finally hit on. The Roomba is probably the most profitable robot on the planet, but at some point was superseded by, as you can imagine, the Amazon bots. Okay, so the Kepler, as you can see, pretty small, pretty cheap, pretty old, but it is the progenitor of a lot of state-of-the-art robotics to this day. Okay, here's another example of, in this case, in the center left, a very small visual module placed on top of the Kepera. This is not a camera. This was difficult to do in the mid-90s. This is instead what's known as a linear vision module. This little box here sends out a bunch of infrared beams, sends out 64 beams in array, and looks to see how long it takes those infrared beams to travel outwards and come back to the robot. The longer it takes that beam to return, if it returns at all, tells something about how far away an object is in front of the robot. So let's imagine we take this little Kepera with this linear visual module, and let's imagine we place my cell phone in front of it. From the point of view of the Kepera, it would see from left to right here that the beams never returned, but towards the center of its visual field, the beams returned with a certain time delay. Those beams had hit my cell phone and returned. So that's what the robot sees at this point in time. Okay, we've got 2 minutes left, so I will just start to introduce this experiment. This was the first evolutionary robotics experiment. No physics engine, so we have to deal with the physical Kepera, which you can see here. They placed it on a table. They were able, because they were doing tabletop robotics, they could make little environments around the robot. It was attached by a tether back to the computer, the desktop, because of course you can imagine in the mid-90s it was very difficult to do a lot of computation on board the robot. So the robot would sense with its linear visual module here, send those numbers back to the computer. The computer would simulate the neural network and figure out what motor commands were required. In this case, there were 2 motor commands. the desired velocity of the turning of the wheels. So the two numbers arriving at the output of the neural network were sent back along the tether to the Kepler robot, and the wheels, the two motors attached to the two wheels interpreted those numbers as desired velocities and would apply torque to rotate the wheels forward or back, depending on whether those are positive or negative numbers. And the robot would start to move. Okay, that's the neural network. We'll talk about the evolutionary algorithm next time. You have a quiz due tonight. You're working on assignment 4. Have a great rest of your day. Thank you.